the CO2 dissolved increases over time because now CO2 is transferred from being trapped in by the hysteresis trapping to be dissolved into the brine. All right, so perfecto. I think that's it for standalone case. Now let's compare it with the limited case. Okay, and as usual, drag them onto the dashboard, 3C and 3B. Okay, sorry. Okay, wait, sorry. Or maybe I can drag the 3C onto this 3B instead. All right, so it becomes better. But of course, I prefer looking at the 2D view, IK 2D view for both of them. Okay, perfecto. Now let's compare the pressure profile. Let's squeeze it first. And then, okay, display, play. Okay, so on the left side, we have limited. The pressure goes up right away, instantly, because you inject something and the volume is actually limited, so the pressure will rise. Whereas on the right side, we have infinite case. So you only inject CO2 within a period of 1 year, it rises up, it barely rises up, okay? Because yeah, you have a very big aquifer. The 1 year injection means almost nothing for the aquifer in terms of the pressure. Okay, and then we go to, as usual, gas saturation. Let's compare them. Okay, now on the left, it's shorter because you only inject 1 year and you have limited, you have the constraint of the aquifer pressure, but we can inject more in the case of infinite aquifer because, you know, the pressure barely changes. So we can inject more CO2. We have more space. We have more capability to store more CO2. So we can have more CO2 injected. So that's why you have the, you know, the CO2 longer, CO2 plume longer at the top for the case of infinite aquifer. And as usual, go behind and then this one, it will have the same explanation. CO2 here is quite short because you activate solubility trapping, but the amount of CO2 is not much. All right, so yeah, the CO2 can only be, you know, the CO2 is trapped only in this zone. But at this zone, yeah, you activate solubility trapping. It, you know, it hinders the movement of the CO2 more, but basically you inject more CO2. That's why you have more CO2 at the top like this. All right. So this is because on the right side, you can inject more CO2 because the pressure is relatively constant. Whereas on the left side, the pressure, you know, increases significantly, increases sharply. So you have, you know, you have no room to inject more. Okay. And let's see the water mass density. Okay. Now, because you have more chance to inject more CO2 in the case of infinite aquifer, you have time to experience the convection. Okay. Again, you know, many, some of the CO2 saturated brine, because they are heavier, they will go down due to gravity. So that's why we have the profile like this. Okay. It's very interesting. And lastly, water mole CO2. Actually, on this side, you also have convection here. But because the amount of CO2 is much less, so it's not that clear whether we have convection or not from the pattern here, from the visualization here. But indeed, we have convection here, where the CO2 saturated brine, due to it being heavier, it goes down. But it is much more clear here in this infinite case. Okay, so that's very interesting, and I think that's all. So in this case, we have completed the case of structural plus hysteresis plus solubility trapping, right? And we have performed the computation for both the limited aquifer and for the infinite aquifer. The best, or the distinct feature of solubility trapping in infinite aquifer, like what we have on the right side, is that we will have clear convection, okay, where the CO2 saturated brine will go down due to gravity because they are heavier than the normal brine, and the normal brine, because they are lighter than the CO2 saturated brine, will go up due to buoyancy. And in this way, we will have more and more CO2 being trapped. It increases the CO2 storage efficiency. Okay, so I think that's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching, and see you again in the next Eng-Man videos. Thank you.